of the MMIX Visual Debugger, which is a GUI-based debugger that allows you to run programs for the MMIX architecture or computer, and we'll be able to try out a lot of the instructions that we would have seen in the first half. So let me. So this is our third meetup. By the way I've planned it out, I've already posted the schedules for the next couple of meetups, but I think that in total we'll have 4 meetups on MMIX, and that should cover enough of MMIX that we can understand, write, and follow simple programs, and enough for us to move on to the algorithms and data structures sections of TAOCP itself. That'll be chapters 2 and 5. And we'll do a few of those, and at some point we may need to come back to MMIX for some more advanced topics like subroutines and coroutines. And then we'll go on to other more advanced algorithms and data structures. So that's sort of the idea. Okay, so we did this and we did this. So this is our procedure. We read a couple of pages, just enough for about 5 minutes time. If there's a little bit more that needs to be covered, we'll go to like 7 minutes or 8 minutes. If there's a little less, we'll just do 3 minutes. At the end of that reading period, and by the way, while we're reading, everyone is encouraged to enter their thoughts and comments, questions into the chat. I will be copying the chat and posting it to our GitHub repo at the end. But then when that period is over, we'll start discussing what we just read. If there's anything to be clarified, or somebody has any sort of comment or response, you can enter it into the chat, or we'll just speak and converse. And so that's the procedure, and we'll just keep repeating that 4 or 5 times. So here's what Knuth said about MMIX. And so with that, if you could turn to this Fascicle 1 MMIX booklet, and we are going to start with the preface, which is pages 3 to 5 in Roman. And I've got a couple of snippets on the slides as well. So the first line, the first snippet is the beginning of the reading that we're going to do, and then the second line is a snippet from the end of that piece that we're reading.
Sorry, is this book posted in the GitHub? Was it?
What is posted in the GitHub?
This is a different book. Page number looks different.
Yeah, so this is the Fascicle 1. So this is a separate booklet that if you Google it, you should be able to find it.
Thank you. I got it in the chat.
I'm sorry. Did you find it?
Miguel posted it in the chat.
Okay.
I'll take it.
All right.
Thank you.
And yeah, so this is sort of the sort of challenge that we're facing, because TAOCP itself refers to a computer that Knuth originally designed in the 1960s, which he himself says is obsolete by now. So it's very difficult to use it now and also understand all the algorithms and stuff like that. So Knuth came up with this updated version of a computer that he feels is like the best possible for his purposes, and he called it the MMIX. This was in the late 90s, and it sort of stabilized in the early 2000s. And so that's what we'll be doing. And then we'll be using that instead of the original mix.
Thank you.
Okay, so does anyone need any more time? Cool. Um, what do you guys think? Any comments? This would be more of a comment sort of section, especially on page 4, where he gives those 5 bullet points justifying his decision. Any thoughts on that? Do you agree, disagree for his choice, with his choice? Jason wonders if the series will ever be finished. Um, yeah, what do people think?
I'd be very surprised considering how thorough he is with all his topics. But I think he has maybe graduate students helping him as well. So hopefully the project will continue over time.
That's actually a really great thought, right? Like, who would be Knuth's successor when he does decide not to continue this anymore, whether it's in his, voluntarily or not. Maybe he should designate a successor, like how CEOs do. There should be a succession plan. Any other thoughts on, he states his numbers as powers of 2. That's what Yuri says. Yeah. 256 reward. Right, right. So that would be 2 to the 8th, I guess. 128 page Fascicle. Wow.
Oh, very
You're
nice.
finding a lot of cool patterns in there. I found it particularly interesting that he collaborated with John Hennessy and Richard Sykes uh, for designing when designing the MMIX. And there's a couple of things that struck me about this. So the first thing was Knuth himself is purely a programmer. I don't think he's actually ever worked at the hardware level or dealt with computers at that level, at least maybe in industry. I don't think so. So it's kind of rare, in my opinion, for a programmer to design like a whole computer, right? So that it's very interesting now that we'll go through MX to see sort of where he's coming from, what his priorities are. And I think generally when new computers are designed, which is relatively rare to begin with, um, I don't know if they have a lot of software people. They may, I'm sure that they get input from software people, but I don't know if they're actually part of the designing team. So in this case, definitely a programmer designed computer. So that's very interesting. John Hennessy, some of you may know that he co-wrote the standard book on computer architecture, and it's called, I think, Introduction to Computer Architecture or something like that, but it's sort of the standard college level textbook. And in that book, he also designed, along with his co-author Patterson, um, a computer for their purposes, for educational purposes, called the Deluxe. It's written DLX. It's also a RISC style computer, so reduced instruction set. And so, with MMIX, you can definitely see his influence there. And Richard Seitz, I have heard Knuth say that he was the designer of the Alpha computer, which was produced by Digital Equipment, I think, which Compaq bought out later. So yeah, DEC, exactly. Um, Yeah, so Yuri says father of MIPS 2000 and now chairman of Alphabet. So you're referring to John Hennessy, I assume. Yeah, I think he does have some involvement with Alphabet, which is the parent company of Google, but I'm not sure what. So he's probably this chairman. Michael says, I would like to see a comparison between MMIX and a modern 64-bit processor like Pentium or maybe PowerPC. I think there are lots of differences. Yeah, if people are familiar with those two chips, anytime you have something to add, feel free to do so. We would all benefit. And remember, all of this is recorded. It's on YouTube. We have all our notes and chat copies being posted. And over time, I'm really hoping that we can build up this repository of information so that people at any point in the future interested in TAOCP can pick this up and find it useful. The only thing about Pentium is that Pentium, the 64-bit Pentium at least, is sort of an extension to the 32-bit computer, the x86 computer. And there was a huge controversy over how x86 ought to be extended. This was in the 90s, maybe even the late 80s through early 2000s. So there's a lot of material to understand over there, definitely. I'm not as familiar with PowerPC, although I believe that it is also a RISC style architecture, reduced instruction set, whereas x86 is definitely not RISC. It's the opposite, or sort of the alternative style, which is CISC, which is complex instruction set. So Michael says things about real processors that you would never learn if you study MMIX, especially how the processor interacts with the OS. Right. Okay, so let us move on to the next set of pages, which is going to be, if you jump past the table of contents, it's section 1.3 prime and section 1.31 prime, pages 2 through 4. The prime, if you notice at the end of the section numbers, is there to sync up with the corresponding section in the actual TAOCP book. So 1.3 prime here is the replacement for 1.3 in TAOCP, and similarly. So we'll have about 7 minutes till about, let's say, 2:40, because there is a little bit more material over here. Okay, does anyone need more time? Great. So, any comments so far? Anything to clarify about the binary representation of numbers using hex?
I have a question about Unicode, not being too familiar with Unicode.
Okay.
He says that it's possible to, I guess, distinguish ASCII from Unicode by putting a leading byte of 0 before the ASCII representation. And I'm wondering if that is foolproof or if there are any Unicode characters that could be confused because they happen to have 0 in that position.
So he says ordinary ASCII are represented by simply giving them a leading byte of 0. So here's what I would say about this little piece about Unicode. When he wrote this, I think this must have been a little early on, because one of the notations that he uses, UCS2, is not in favor anymore. And it gets a little complicated with Unicode, but the idea with Unicode is that we're going to allocate a whole bunch of numbers, something like over 1 million numbers, and we will assign, every character in the world for every language one of these unique numbers. Now, ASCII being a 7-bit encoding of the common English letters and numbers and punctuation marks, so on, that only needs 127 numbers, right? So from 0 to 128 numbers, so 0 to 127. And so what they did was they said that we will reserve that. So, 0 to 127, even in Unicode, is going to be exactly what ASCII is. So then there's no conflict there. So now what happens is that you've got these extremely large numbers for characters that are not ASCII. These could be Chinese ideographs or Arabic letters and other, languages that are not that well known throughout the world. And when you start representing these huge numbers, obviously, 1 byte or 8 bits is not enough, right? So you could use 2 bytes. It turns out that even 2 bytes is not enough, right? Because even with 2 bytes, you can only go up to like 65,000 different unique values. So you end up needing like 4 bytes. And originally it was even more, but nowadays they fixed it at 4 bytes. So now the question is, how do you actually encode a large number into 4 bytes? And there's various ways of doing this. The way that he's talking about uses 2-byte pairs, and that nowadays is called UTF-16 and not UCS2. So if you were using UTF-16 and you had, let's say, 2 bytes that you could use for certain characters or pieces of characters, then how do you represent ASCII in that? Well, you just make, the first byte 0, and then the second byte will have that 7-bit piece in there. So that's what he's talking about. But again, what I would say is that this paragraph actually is showing its age, and I wouldn't pay a lot of attention to this. If you're really interested in Unicode, there's a lot of other material that has superseded what he's talking about. But as far as his intent goes and the main thrust, he's right. Like, there's all this stuff that was standardized that allows us to use a single way to represent all the languages in the world. Anything else? Um, did you catch the hex notation that he will be using the pound sign to denote hex numbers? Because for a lot of people like myself, I'm just used to 0x or just x. So the pound sign is kind of different for me. And let's see what else. And his nomenclature, right, which is definitely, these are Knuthisms, the octas and the tetras and the wydes with a y. So you just have to sort of get used to this. Do people have some other preferences that they've used in the past or currently for these, um, you know, 2 byte, 3 byte, 4 byte, 8 byte groupings? D word for tetra. Okay, that's what Yuri says. Um, yeah, so there's definitely a lot of choices there, but throughout his book, he uses these. And let's see, two's complement. Anything to clarify there? People pretty familiar with that? Could somebody, I don't know if he, Knuth just says, how do you perform two's complement? Well, first of all, two's complement would mean, or using two's complement, if the leading bit is 1, it's going to be a negative number. If the leading bit is 0, then it's a positive number. And how do you take the 2's complement of a number? You just subtract 2 to the n. So in this case, because these are 64 bits we're talking about, if we have an octa, we would be subtracting 2 to the 64 from whatever that number is, and you would get the 2's complement. Does anyone know of any other way that would be easier than doing subtraction to get the 2's complement?
Isn't there some way you can flip the bits other than the leading bit, and that positive number is the negative equivalent? That thing, or maybe I'm wrong about that.
So you flip the bits and then?
It's a positive number in binary, so you would add up the 2 powers of 2 for every 1 bit, and then flip the sign of the positive number.
Okay, I think that you may be describing it correctly, but I am not following it completely, although Michael has just entered this other technique in the chat, which is probably what you're describing, Jason. And he says you flip the bits and then you add 1. And it works both ways. So it doesn't matter whether it's a negative number or meaning that it has a leading bit of 1 or not. And welcome. So hi, Mark. Great to have you join us. We're in the middle of discussing this section from Fascicle 1, MMIX. And Yuri said the same, 1's complement and add 1. Yeah. So practically speaking, I think these two techniques that Michael and Yuri have described are really easy if you're looking at the bits at least. But in sort of a mathematical sense, what Knuth has described is pretty good. Okay, so we are going to move on to the next section, which is again Fascicle 1 MMIX, which is the booklet by Knuth that describes MMIX. And we're reading section 131 prime, description of MMIX, and pages 4 through 5. And I've got a couple of snippets on the slide for the starting of the reading and the ending of the reading. And we have about 5 minutes till about 2:54. Okay, anyone need more time? Cool. Just wanted to confirm from Mark if he has the text, the Fascicle 1 MMIX, and if you're able to follow along.
Hello, no, I don't have that book.
Miguel, would you mind posting that link again? Oh, okay. Miguel needs one more minute, so we'll give him a minute. And yeah, so Miguel has posted the link in the chat. Mark, you can get it from there and then just follow the slides. Meantime, if anyone wants to enter their comments or questions into the chat. Okay, so here we just read about the memory and the registers that are going to be used in MMIX. And it's a 64-bit computer, so there are 2 to the 64 cells of memory. And he says there's 2 to the 8, that's 256 registers that are general purpose, together with 2 to the 5, that would be 32 special registers. Any comments on this, initial description of memory and registers and how they will be accessed and used? Anything about the notation that we could clarify? Did everyone get the capital M subscript notation, like M sub 2 and M sub 4, M sub 8?
They're the memory locations.
They're the memory locations, yeah. Yeah, so when he says capital M and then it's indexed, that's referring to memory. And then the registers, how are registers going to be referred to? Anyone made a note of that? What are the register names? Yes, Yuri says it's dollar and the number. So there's 256. So they start from 0, go through 255. It's just a little line in one of the paragraphs. And that's the general purpose registers, $0, $1, $255. Miguel says, it took me a second to understand the M sub X. And Michael then is responding to that. Michael, do you want to elaborate or expand on that explanation? Because I personally needed a lot more than 1 second. I needed a lot of time and practice to figure out what he exactly means by that subscript.
So what I understood is like each subscript, you just go like a bigger chunk, right? Like without the subscript is 8 bits. So with the first subscript, like M2, now is just double the size. It's now 16 bits, right? And now you have to count differently because the index has just doubled. That's what I understood.
Yeah, that's if you're accessing 2 bytes, then it throws away the low order bits. So M0 and 1 are the same thing. It throws away the low bit of the 1, and you get the 2 bytes starting at 0 and 1. So it's M2. I should have said, what I wrote up there, I should have said M4 of 0 equals M4 of 1 equals M4 of 2 equals M4 of 3. I didn't put the subscript. I couldn't find the key for it.
Oh yeah, in fact, I would say don't put a subscript because this is going to go into Markdown, and so what I do for subscripts is I put an underscore. It's just my convention. Yeah, because it gets tricky when you're dealing with text. So yeah, I think what you guys are saying is right. But again, it takes a little while for this to sink in, and it did for me. But I think Miguel said, he's referring to chunks. When you have a subscript, it's referring to a particular, and it's not just any chunk. It's a very specific chunk that starts at a very specific place, which is a multiple of that subscript. And if you're familiar with sort of computer terminology, memory terminology, we would call this sort of aligned references, right? Aligned addresses. So what I guess Jason has written, if you have m sub 4 and you give the index 0, we know what that starting address is. That starting address is address 0. And so because it's m sub 4, we're getting 4 bytes out of memory starting at 0. So we are going to get 0, byte 1, byte 2, and byte 3. But if you give the index 1, but still say m sub 4, we're still in that same chunk from 0, 1, 2, 3. And so you're still going to get the same chunk back, even though the index is different. And similarly with index 2 and index 3. Once you go to index 4, that's the next chunk of 4 bytes, so the next tetra. So then, it's a different chunk. If you just apply this to the wydes, so m sub 2, like Miguel has typed into the chat, same thing applies, right? So we're always dealing with these chunks. They could be 8-byte chunks, or 4-byte chunks, or 2-byte chunks, or a single byte chunk. If there's no subscript, what does that mean? If it's just plain m?
Default is 8.
Is that right? I think it's a single byte. I think m without a subscript is the same as m sub 1. And I think he wrote that somewhere, but I can't locate it that quickly. If somebody finds it and confirms it, that would be great. Okay, so
Sorry, I don't.
Yeah.
Where do I see the subscript in this example? Is it covered in page 4 or 5? I don't see this m underscore.
Yeah, it's at the
notation.
bottom of page 4.
Okay.
At the bottom of page 4, exactly. Yeah, and the underscore is just what we're using in the chat because we can't enter a subscript. At least
Okay, I
not
see.
that easily
Okay,
in the chat.
got it. Okay.
So yeah, bottom of page 4 is exactly right. And I guess the very last thing would be the special registers. They have unique names. There's no pattern in that case. So they're called RA, RB, RC through RZ, and then there's BB, TT, and so on. So each one of these special registers serves a very specific purpose. So you can't just use it for any computation. They're going to be used in a very specific way. But he does mention RA and RR. So RA is when you get arithmetic overflows, for example. This register will indicate that, and RR is for the remainders. Okay, so let's move on to the next few pages. This will be pages 5 through 6. And it covers the section that begins, that is titled Instructions. Okay, this was a short section, but it is introducing the instructions. So there's quite a bit to process over here, and it's already a little past 3. So let's take a 10-minute break till about 3:19 East Coast time. And when we come back, we'll discuss this section. So again, please feel free to turn off your webcams and just relax, and we will see you in a bit. Okay, we're back. Any comments on this section that introduces the instructions in MMIX? Yuri says only 256 opcodes. Is that only in the sense of there's just so few, or is that some like comment that it's not enough? I'm not sure. Few. Okay. Compared to what, by the way, Yuri? Modern processors. Miguel says add of the 3-register form reminded me of Lisp. And how's that?
You know, the operand, then the body, so you start with the name of the function and then everything else, right? Including inputs and outputs and everything.
Okay.
So
Do you remember the syntax? Could you maybe paste an example from Lisp? So it's so what you're saying is sort of like the prefix notation as opposed to the infix notation. Mm, okay. Any other comments? Again, there's a lot of new notation over here. Did everyone get the notation? You don't have to get everything right away either. This is just sort of introducing the format, and until you actually work with it, which you may have already, but I know for me, I kind of read it, but didn't really understand it thoroughly until much later. Yuri says he uses GNU style assembly left to right, as opposed to Intel style assembly for the operands, which is right to left. Oh, okay, interesting. All right, so let's then move on to some actual instructions, which is the next section titled Loading and Storing. This is pages 6 through 8. Okay, anyone need a little bit more time to read the section? All right, so what I'm going to do now is, so feel free to continue the discussion in the chat, post any comments, any questions you have in the chat, or speak up. But I felt like I'm just going to go ahead and show you these instructions in action, sort of this hands-on practice. And if you have any questions about a particular instruction or the way the instruction is used, just interrupt me and ask a question or type something into the chat. So what I'm using for this demo is this MMIX Visual Debugger. And it was written, I think, mainly by Martin Ruckert, who wrote the MMIX supplement book. And you can see that it's this standard, Windows style application. And I believe that there are binaries for Linux and Mac as well, although I have not tried them myself. And it seems to work pretty well. So even though I think the last update was a while back, but it works pretty well. The documentation is also not that bad, so you can go to the help and there's this window that pops up. Oh, I guess it's not going to show in my screen share, but yeah, that's fine. You can look that up later. So what you do is once the app is open, you open a file that is a program file, so written in MMIX assembly, right? And MMIX assembly programs have a particular format and syntax that is not just the instruction. So there's other stuff in there, but it's not that complicated. And as we go on through these meetups, I'll introduce more and more of that stuff. So by the time we reach the 4th meetup, we should be well conversant with MMIX assembly. The file that I'm going to use, I've actually, oh, this is not the one I wanted. I've actually posted it to our GitHub repo, and the link is down there in the chat, so you can also play with it. So here's what the file looks like. I'll just quickly scroll through this so you can get a sense of things. This is sort of the first 40-50 lines, and next few lines. Okay, and so about 225 lines. There's a lot of comments in there, so there's actually not a lot of instructions, but each line of executable code is a single instruction or some sort of directive for the assembler program that's going to run this thing by compiling it to object code. So let's go back to the beginning. And what I've got in this file are just the load and store instructions that you just read about. So you should be able to see every single instruction that you saw in the text and an example of that. The comments, comment lines can begin with any non-alphanumeric character. So as long as the first character of the line is not a letter or a number, it's going to be treated as a comment. But do not use semicolon or pound signs to start a comment line because there are certain exceptions that apply to those two characters. So it's just better to not use them at all for comments. I'm using C++ style comments, but that's my preference. There's no multi-line comment block, so you have to make individual line comments if you want more than one line of comments. Each statement, so for example, this is one statement that I'm calling a statement. At the end of this statement, so like at this point over here, if you give a space, then everything after that is ignored. So you could actually just write comments in line at the end of that statement if you give a space after that. So that's another way to do comments. When this program is loaded, so what's happening in this debugger? The debugger has two pieces in it. One piece is the assembler, and the second piece is the simulator. The assembler is going to take this textual program, and it's going to translate it to machine code, and that generates a new file, and it's called an object file. That object file is then handed to the simulator that's part of this app, and the simulator then starts to execute those instructions. When the object file is loaded into the simulator's memory, it's loaded at address 0. So if you look at this line 19, this is the first valid MMIX instruction. The only thing is that this is actually not an instruction. The word byte is not part of MMIX itself. This is part of the MMIX assembly language, which says there are certain things that you can tell the assembler to do to sort of prepare the program to run. And the byte pseudo-operation, that's what Knuth calls it, the byte pseudo-operation tells the assembler to place a certain value into memory, wherever that memory happens to be. So as I mentioned, the program starts out at address 0. So when I say byte hex 12, it's going to take the value hex 12, which is 16 plus 2, 18 in decimal, and it's going to place that into the first byte at address 0. The second instruction is going to be another pseudo operation, and it's going to place this byte hex 83 into the next valid address, which is going to be address 1. So the second byte is going to be hex 83. Any questions so far?
So hex 83 is the value which is getting placed at address 1.
Yes. Similarly, the third byte is going to be set to A7. That's hex A7. Okay, now line 31. In line 31, I don't have a byte pseudo-op. I have a wyde pseudo-op. So a wyde, as you know, as we just read, is actually 2 bytes. Now, the way 2 bytes work, or a wyde works, is that it has to start at an address that is a multiple of 2. This is called 2-byte alignment, even though Knuth doesn't use this term, but that's what generally people will say, that wydes are 2-byte aligned. So we've got 3 bytes in memory already, right? Address 0, address 1, address 2. Address 3, which is the next open memory cell, is not a multiple of 2. So you cannot place a wyde starting at address 3. The next valid open slot for a wyde is address 4. So even though I don't have any instruction for the 4th byte, which is address 3, the assembler will automatically place the wyde starting at address 4, which is the 5th byte. Everyone got that? Okay. The same thing.
One more.
Yeah, go ahead.
So when the line number says byte, assembler automatically assigns it to address 0. We don't have to do anything, right?
Because
Assembler takes care of it.
because the program as a whole starts out at address 0. So unless you give a specific address directive, which I did not, the program will start at address 0. That's the reason.
Okay.
Yuri is asking, does MMIX store in least significant byte or most significant byte order, or rather interpret the opcodes instructions? So MMIX is a big endian architecture. So that'll be most significant byte order. And you will see this in memory. I'll show you the memory and it'll become really clear. That's why I feel like the debugger will help us a lot. So let's scroll down a bit. After the wyde that I've placed in address 4, this is going to take up 2 bytes, right? So address 4 and address 5 will be occupied by the wyde. The next open slot is address 6. But if you notice, my next instruction actually is asking to place a tetra, which is 4 bytes. So a tetra can only be placed at an address that is a multiple of 4. So the assembler will not place this tetra value that I've asked it to place into memory at address 6. It cannot do it at address 7 either. So the next valid starting address for a tetra is address 8. So this value is going to be placed into 4 bytes starting at address 8. And I've actually shown the bytes over here. That's how it's going to be. And this, I think this is, this also addresses Yuri's question. All right, next directive is for an octa. Same alignment restrictions apply, but an octa is 8 bytes, so it has to be 8-byte aligned. So what's going to happen is that the tetra that was placed into 4 bytes starting at address 8, which means 8, address 8, address 9, address 10, address 11, right? Those are taken up by the tetra. So the next open cell is address 12. But 12 is not a multiple of 8. So that means all the addresses from 12 through 15 are going to remain empty, and this octa will be placed at address 16 because that's the first valid multiple of 8. And then I place another octa right after that, and there's a reason for this particular value that I'll explain later. All right, so now let's look at the actual code. So far, I've only placed data into memory. Where are the instructions? So the first real instruction is on line 61. And line 61 also has a symbol name associated with it, this word, me. This is required. So all assembly language programs for MMIX have to have a symbol that is case sensitive, starts with a capital M, and then lowercase a-i-m. Otherwise, you get an error. Wherever you write this symbol name before the instruction, and it can be anywhere before the instruction, sorry, it can't really be anywhere. It has to start in the first, at the first character, because otherwise it becomes a comment, right? So anywhere meaning that it starts at the first column, but then you can have as many spaces after the symbol, and you can have the instruction. So this instruction is now associated with the symbol main. And that's just to get the program started. So the simulator knows what is the first line of, or where's the first instruction that it actually needs to run. So this first instruction is an LDB, which we just read is a load byte signed, right? We had the loads and the stores, and they're divided into or grouped into two separate categories: the ones that deal with signed numbers and the ones that deal with unsigned values. So the unsigned values have a U suffix, and the signed variant does not have a suffix. All right, so this is the general form of an MMIX instruction. You've got the opcode, and so Yuri's got a question. I'll come back to that in just a second. Then you've got the three operands, right? The three operands are these registers. And if you remember, registers are referenced using $. And so could somebody say what the load byte is going to do over here? What's the meaning of this instruction?
So what I understood is it computes this A thing, and from whatever that address is, whatever is in that address, puts it in the register 4.
Yes, that is absolutely correct. What is the A thing here? How is that computed? Anyone want to explain? What's the address that's going to be used to retrieve the value? It's the address, yeah. So Yuri says it's the address. And Yuri also said in an earlier comment, it's what's in $2 plus what's in $3. So you add the contents of $2 with the contents of $3, you get an address, or it's treated as an address. You go to that address, you take whatever's in that address as a byte. You take the byte at that address, essentially, and you put that byte into $4, which is the destination, right? The first operand is the destination, and the next two operands are sort of the inputs. Okay, let me go over the chat.
Sorry, I didn't understand. What is there in $2? I understood the destination is $4, but $2 is the memory address, or it is the content of $2?
Okay, so that's actually a great question. I did not go over these comments just before. So if you look at lines 47 through 59. Okay, so let's do that. When the program starts out, we have these 256 general purpose registers, right? And they're all numbered 0 through 255. Pretty much all of them are 0 when the program starts out, except for a few. So $0 is what we programmers call argc, which is the count of the arguments to the program on the command line when you ran it. This program does not have any arguments. So when we look at $0 later, you'll see that it will be 0. But if I had run the program with, let's say that it's a program that reads a file for input, right? So it would have just one argument, and then $0 would be 1. Okay. Actually, I think I'm.
$0 is the program name. $1 is the first.
$0. Let me see.
Is it the cell?
No, $0 is the arg count. I'm just wondering if the program name itself is always an argument or not. You know, I can't really remember.
In shell,
right
at least
now
$0 is the name of the program.
No, $0 is definitely the count of the arguments. I'll explain where the program name comes into play. So $1 is the address of the arguments themselves. So if you had, one argument, $1 will be the address where the actual characters of those arguments are stored. So it's a pointer to a string, $1. So if you had like 3 arguments for the command, let's say 3 different words, then $1 will be pointing to the first word, and then these are null terminated strings, so there's 0 byte after the first word, and then the next word will be the second argument, the next word will be the third argument. How do we know how many arguments we have? From $0. That's the argument count. Okay, $255 is also special. And I'm going to explain that probably in the next meetup, but it's what's called the first global register. And these are registers that are available in all contexts of the program. And again, we don't need to know this right now, but I just want to point this out, that this is another one of those registers that will not be 0 in the beginning. So that leaves $2, $3 up to $255. All of them are 0. So I'm using that fact over here. I'm using the fact that $2 and $3 are 0. So when that address is computed for line 61, it's going to take the value in $2, which is 0. It's going to add it to the value in $3, which is also 0. 0 plus 0 will give us 0. What is at address 0? It's this guy. This thing is going to be loaded into $4. Is that pretty clear?
Yes, thank you. Yeah.
Now let me go back to the chat. So Miguel asked, I think I've answered that. Isn't $2 and $3 empty yet? Michael says copy 1 byte from memory. Yuri asked a really interesting question. He says, what is the initial value of program counter? Could someone explain what a program counter is? Maybe Yuri, you could explain that? If somebody else knows. Okay, Yuri says it's the address of the current instruction to execute. Okay, so the program counter is basically it's the name for whatever it is that tells us what is the next instruction to run, right? Sometimes this is a register itself. In MMIX, there is no program counter. So the program counter is something that the simulator is supposed to somehow manage. Knuth doesn't talk about a program counter. And it's not visible to us in the debugger. It's sort of hidden in the application itself. But I will show you a way that you can sort of work around this program counter thing if you wanted to play with it. But that'll be in another meetup. Okay, what else? argv of 0 is the name, I think. Yeah, I have to confirm that. I'm not sure about the program name, whether it's always at arg, because I don't think I saw that. But anyway, we will see. So Yuri asks, can we assume all opcodes execute in 1 clock cycle, whatever that means in this context? That's a great question, but it's a little ahead in terms of our content. We will get to timing, I think, in the next or the meetup after the next one. So Knuth has a specific section on timing, and you can look it up if you're interested. Just search for the word timing, and he'll tell you what the sort of performance or the timing cost is for these instructions. Okay, so now I'm going to run this program, and we will now start to see what's going to actually happen. So to run the program, what you do is, if you look at the MMIX menu, by the way, is the font big enough? Is it pretty clear? Okay, so you'll see these choices: assemble, debug, step instruction, etc. I'm going to select debug. Hopefully it will just run. No, it didn't run. If you get this error, sometimes you do, it says no MMS file selected for loading. There is a file in here, so you are going to go like, what is it talking about? The reason is that sometimes it fails to recognize that it needs to run the currently loaded file. So you go to sources under options, and here you'll see a tab for the file that you have open. If you have more than one file open, you'll see multiple tabs in here. Make sure that these two things are checked: the assemble and read symbol table and the load MMO file. And once you do that, the tab gets a red dot, meaning that it is somehow enabled or it's operational. Okay? This is the cause of that error. Sometimes I don't need to do this, other times I do, so I'm not 100% sure what I'm sort of bypassing in some step. But once you do this and you say OK, and then you go back to MMIX and you say debug, it runs the program. Now, unfortunately, I cannot change the font size of these areas on the side. I can only change the font size of the editor itself, which I think is fine. So the other parts may be a little small, but tell me if they're unreadable. So they are at least readable, right? Okay, so you can see these numbers over here. Okay, great. Yuri asks, the label main is required. Yes, the answer is yes. And okay, so that's it. So see what happened? The program began, but the debugger stopped it at the symbol main because that's the first instruction that it will actually run. And so that allows us to now examine what's in memory. Memory is down here. These three panels that are the bottommost panels, that's memory. And it's divided into three panels because these are three different parts of memory that are significant for MMIX in some way. We will not need this last part, so I'm going to just close that window. The way you close a window is you see that X in the top left of the panel. You have to double click it. A single click will not close it. This was so frustrating for me in the beginning. I was like, why am I not right on the X? For minutes and minutes, I kept trying to single click it and it requires a double click. Okay, so the other thing is this black background panel. This has sort of a status of what has happened so far. I don't think that we need this either, so I'm going to close this. And over here, the top right panel, these are the registers. It's only showing 2 because only 2 have actually been used so far. So $0 is what I told you, which is the argument count, which is 0. And $1 is a pointer to argv, which is a special place in memory, which we're not going to look at right now. $255 is again something I told you that will not be 0. This is a special global register. The value here happens to be the offset of this instruction in memory. So the 20 that you're seeing over here in hex, which is 32 in decimal, it's saying that main is at memory address hex 20, and which is actually the case. So that's all it is. And I'm going to close this too because we don't need it. This panel over here are the special registers that you've just read about. And we won't be concerned with most of these special registers for now, except for this one, this RA. That will be kind of interesting. Okay, let's look at memory. So let me go back to the top over here. I'm gonna have to go a little bit over time. I hope that's okay. If anybody wants to bail out, that's fine. But we will probably go on for another 10 or 15 minutes. So if you look at these memory windows, memory panels, they've got two buttons over here. This button, hex, is saying what numerical format it's going to use to display the values. And this button says what is the unit of memory that it's going to sort of display as a chunk. So since it starts out as tetra, you're seeing 4 bytes at a time here. But let me change the tetra to a byte so we can look at it byte by byte. So now I've got it byte by byte. And if you look at my first directive, I asked the assembler to place the value, the hex value 12, into the first byte. And you can see that that's actually what happened. There's a 12 here. And then the next byte is 83. The third byte is A7. The fourth byte, because of the alignment restriction, was skipped. So it's 0. And then the next value is a wyde. That's on line 31. And you can see that that was placed as 87, followed by a 65. Okay, and then we've got, sorry, it's this, 8765 here. And then we asked for a tetra to be placed in memory. And again, because of the alignment restriction, that means we could not use the next 2 bytes that remain empty. So those are 0. And then we've got the 4 bytes, 87, 65, 43, 21. Okay, and let me now switch the unit to tetra, so it's a little easier to understand. So this is the 87654321 tetra. Then after the tetra, I asked for an octa to be placed in memory. That was here on line 39. And what that means is that the next tetra can't be used for an octa. So we skip over that, and then let me switch the display to octa. And we have this octa, which corresponds to line 39 in the program. Okay, and then we have the last octa, which is this 2 followed by all zeros. So those are all the storage directives that I had given. After the storage directives, we now go to the code. So this is the first instruction. This will be placed in the next valid memory cell, right? Remember that instructions are 4 bytes. So that means they have to be 4 byte aligned. They're all tetras. So let me switch to tetras again. If I switch to tetras, then this was the octa that I placed. And this memory cell is a valid tetra aligned address. So the next instruction can start over here. And this instruction you can see as a tetra is 800402003. Let's try to understand them as bytes. So let's switch to bytes and go over here, and then you can see the 4 bytes. What are the 4 byte values? So 80 is the opcode. So that has to be my load byte instruction, right? LDB, that's 80. If you look it up in the opcode table, it should show up as 80. Then I've got register 4. So register 4 shows up as just 4. And then I've got the second operand, which is register 2. It just shows up as 2. And the third operand is register 3, which just shows up as 3. So that's one instruction: 80, 4, 2, and 3. And then you have the second instruction: 81, 5, 2, and a 0, which I'm going to explain in just a minute. So do you see what's happening in memory, how the program has been laid out? Any questions? Let me go over the chat. Oh, okay, no questions in chat so far. So, okay, so let me just move on then. Let me switch to tetras. I think that's...
One question.
Yeah.
The second LDB is showing as 81 instead of 80.
I'm going to explain that. Let's first run the first instruction and see what's going to happen. So if you look at the MMIX menu, you've got debug, you've got step instruction, step over, step out, break, halt, run, set breakpoints, and stuff like that, right? If you've used debuggers before, most of this stuff should be pretty obvious to you. If you haven't, I'm just going to go through them very, very slowly as we use each one of these things, and it'll become very clear. I'm not going to use the menu. I'm going to use these buttons over here in the toolbar. So this button is the debug button, which I essentially ran the first time. This next button is a step instruction. So this will execute one instruction only. So I'm going to do that. I'm just going to tell it to execute the instruction at line 61. So let me do that. I click, and you see some things turned red. Red indicates a change in the state of the simulator. What has changed? What has changed is that, sorry, it's not even just what has changed. It is what has been used and changed. So what was involved in the instruction that was run. So I'm not sure why $3 is not highlighted. But anyway, we can see in register 4, which was 0 before, it wasn't even being shown. $4 now contains the value hex 12. And we know it's hex 12 because over here I've got the same buttons that allow me to display the format of the value. So if I change this to, this is for characters, this is decimal unsigned, this is signed decimal, this is floating point, and this is back to hex. Okay, so that's what we expected to happen. We had asked for a hex value of 12 to be placed in the first memory location, and then when we ran this instruction, the address that was computed was the first memory location, that's address 0, and so it took a byte from there and it placed it into this register. The register, remember, is a 64-bit register, so it's actually an octa. And if I show it as a byte in byte format, you can see the 8 bytes, and then this is the first byte. Now, keep in mind that registers are shown in this big endian format. So the most significant byte is, on the left, and the least significant byte is on the right. Okay, so we took that 12 byte and byte value and then placed it as the first byte of register 4. Any questions about this instruction? Okay, the next instruction you'll see has a, so Deepa, I think, noticed that the opcode was different from the first instruction, even though the symbolic name is the same, right? They're both called LDB. Why is the opcode different? One has opcode 80, the one that just ran, and this next one has opcode 81. The reason is this thing here. Sorry, not here, this one. This is the next instruction. So you'll notice that this is something we didn't cover yet. It comes in a later section, but there's a whole bunch of instructions that allow you to use constants instead of a register for computation. So the first instruction used this register 3, and the address was computed by taking whatever was in register 3 and adding it to the value in register 2. This register 3 can be thought of as an offset to some base address, and the base address is what's in register 2. So think of an array, right? An array of values in memory, and the first index of the array can be thought of as being at the address of the array itself, or at index 0 from a base address. And then the next value can be thought of as at index 1 or offset 1 to the base address. So it's the same thing over here. You can treat a single address as some sort of base address and then keep adding values to it. And if the offsets are small enough, you can actually use constant values instead of using a register. So I just used a constant value of 0 here. So it's saying take the address in register 2 and add the constant number 0 to it. You get some new address and go to that address, take a byte and load it into register 5. So when I run this instruction, I should see the same value 12 show up in register 5. So that's what I'm going to do. And you see that's what happens. Yuri asks, why did RL highlight for the instruction on line 61? So this is again one of the more advanced topics, but there is the concept of local registers in MMIX. And what RL is saying, all the registers up to 6, below 6, or better to say, what is the next local register that's available? And that's register 6, because the registers 0 through 5 have been used and used locally. So that's what it's referring to. It's a little more complicated concept that I'm not sure if we will need that right away, but that's what it means. So, from a practical point of view, you don't need to be concerned with that right now, but because it does change, it will show up as highlighted. All right, so we're past 2 instructions. Let's look at the third instruction. And this is going to take the address in register 2, which is still 0. It's going to add 1 to it. So we should get address 1. It's going to take the value at address 1, which we know is, let me switch this to bytes, which is 83. And it's going to place that into register 6. So we should see register 6 show up over here with the value 83. And so let's do that. But that's not what happened. Could someone explain why it's not just 83? When we ran this instruction, why do we see all these F's in register 6? Yeah, Yuri has the answer. The sign bit was set. Which sign bit do you mean, Yuri? Yeah, so Michael also explained it. 83 is a signed byte. Well, 83 by itself is not a signed byte, but 83 does have its high bit set. The instruction we're using to load 83 is a signed instruction. It's load byte signed. So it's going to treat that value 83 as a signed number. And what happens with signed numbers is that if you put them in in a location that has more bits than what is needed just for that thing, then it's going to sign extend. It's going to take that high bit and copy, make everything to its left one. So yeah, so the sign was extend. So this is some negative value, right? Hex 83 treated as a signed value. You can compute that. It's some negative number. You subtract, 256 from whatever 83 is in hex, and you get that value. Anyway, so you get sign extension because we use load byte. Let's look at the next value. Next instruction. The next instruction is going to ask for a byte from address 2, which is going to be A7 down here. A7 also has the high bit set, right? It's greater than 127, whatever it is, right? And so if I use LDB, I would get sign extension, but I'm using LDBU, which is the unsigned load byte. So when I run this in register 7, I should get just A7. Any questions so far?
Yeah, kind of a general question about the register's most significant byte versus the memory's the byte ordering, most significant versus least significant. I'm curious why when we're loading in A7, it's showing up at the rightmost position in the register as opposed to the leftmost position in the register.
That's just the addressing in the register itself. The register is laid out so that the bits, the most significant bit is on the left and the least significant bit is on the right. So if you number the bits from 0 to 63, bit 0 is the rightmost bit and bit 63 is the leftmost bit. That's just the way the register is laid out.
And that's opposite than the memory on the bottom of your screen?
It's not really opposite or the same as memory. It really is saying in memory, you've just got some bits laid out. How you get them out of memory will depend on the instruction that you're using. If you're just getting one byte out, then it's going to be placed into the least significant byte on the rightmost side, right?
Got it.
If you're getting 2 bytes out, then in memory, the first byte comes before the second byte, right? Memory is left to right, like just in normal order. And so when you take those 2 bytes out, they're going to be taken as a chunk and copied into the register from the right-hand side.
Got it. Thank you.
Okay. So anything else? Okay, I'm going to skip over very similar stuff, but just it goes over the wydes and the tetras and the octas, and you can look at this yourself because you have the debugger available and you have the file available and you have our recording available and notes. I'm going to go over to the stores. So what I will do is I'm going to set a breakpoint here. I will set a breakpoint here. So if I click in this column, you'll see this blue dot appear. And that will just run through all of the instructions up to line 143. And for that, I will use this button, the debug/continue button. And you will see a whole bunch of things turn red because it's going to run through a lot of instructions. And there. So let me, okay, so let's scroll down here. Okay, So what has happened here? There's a whole bunch of instructions that actually, set a lot of registers. And so you can see over here, there's a lot of changes, right? Let's make this octas there. So all the storage directives that I had, data from there got loaded into one or the other register over here. Now what I'm going to do is run through some store instructions. Store instructions take values in registers and place them into memory. So this is the write equivalent of the read instructions that we saw earlier, right? So what's the first instruction going to do? This is a store byte, and this is signed. And so it's going to take the, okay, so it's again got 3 operands. And again, the third operand I'm using is a constant, right? The general format is the same. The last 2 operands are used to construct an address. Now, how is the address going to be used for a store? This is going to be used in the opposite direction. So we're going to take something from some register, and we're going to go to the address that we have computed, and we're going to write to that address. So the result of this is going to be, take the value in register 4, go to the address computed from the value in register 3 by adding the constant 0 to it, and write the value in that location in memory. If you remember, I had asked for this special value, 2 followed by all zeros, to be stored at one of the locations. This was loaded into register 3 at some point. In an earlier instruction, I did that already. So now I do have this 2 followed by all these zeros in register 3. The reason why I'm using this special address is this is the valid part of memory where a program can write data. So a program is not allowed to write data below this address. So I can't just use any address. So think of it as, programs that are running in your computer, they're not allowed to write to just any arbitrary address because those are security risks. There's data corruption that can happen. There's a lot of other things associated with those restrictions. So that's why I needed this value in some register. So I did that. It's in register 3. I'm going to use this as my base address from this point on. And the offset in this instruction is 0. So if you look at this bottom panel over here, this starts out at that very address, the 2 followed by all the zeros. This address has a special name. It's called the data segment. It's over here, the data segment. So from now on, we'll talk about the data segment, and it means this address. So for the data segment, I'm going to take whatever's in register 4, and at the first byte, I'm going to place that value. What is in register 4? It's still that value 12 that we had originally loaded. So right now, you can see there's a 0 here. There's nothing. The data segment essentially is empty because we haven't done anything with it. So let me step over this step 1 instruction, and you see here the memory location was affected. Let me change this to a byte view, and you can see the first byte became 12.
Sorry, I have a question.
Yeah.
So STB automatically starts at the data segment location, or it has to be instructed to start at the data segment location? The
Could somebody answer that? Where is store byte? What address is store byte going to use?
the data segment location 2000 zeros. I mean, my question is that a prefix? Okay,
Yeah, I understand your question. I was, I'm a little tired of speaking. That's all. Just hoping somebody could pick up the slack. But Yuri has the answer in chat. The address that every instruction or any instruction will use will be coming from some of the operands. So the data segment is special because if I had given this like if I didn't load that address and I just told it to write to whatever the next address is in one of these operands, like some arbitrary address, I may get an error. The simulator won't allow me to write to certain addresses. So I purposely loaded the data segment address in register 3. Once it's in register 3, whatever that address is, that's what store byte will use, because that's the address operand, right? The address operand are the two, the second and the third operands are used for the address, to compute the address. Okay, Deepa says got it. Great. So, yeah, any other questions about this store instruction? All right, let me just run the next one, which is going to store something at offset 1 in the data segment. And again, it took the value from register 5, which was 12 again. So it stored that here. And then the next one is this one that just ran. At offset 2, it stored an 83. Why? Because register 6 had FFFFF 83, but I only asked for a byte, right? I told it to store 1 byte. So it took the first byte of register 6, which was 83, and it stored it into this location in memory. All right, the next instruction is interesting. I'm going to make this window a little bigger, and you will see what happens. So what is this instruction going to do? It's going to take the value in register 9, which is this value, 1283. It's going to store a byte from that value at offset 3. Let's run this. And did it do what we expected? Did it store an 83 at offset 3 of the data segment? Yes, but Yuri noticed that something happened down here. This register, this special register, which is called the arithmetic status register, got highlighted because it changed from 0 to 40. And the reason for this is that this bit that was set, because it's a 4, that means it was just 1 bit, right? That was set. That bit is called the integer overflow bit. And there are certain computations that you do with instructions that can set the integer overflow bit. What caused the integer overflow bit to be set? The reason is that $9 is, as a register, like the entire register, its value is 1283, right? We're taking a piece of that value, right? We're only taking 1 byte of that value. and we're going to store it into a byte in memory. But the integer overflow exception, or that bit, is set because the number as a whole does not fit into one byte. Does not fit into one signed byte, right? It's a STB, that's a store byte signed instruction. So whenever that happens, that bit is set. And there's various reasons for this, like why you may want to do this. But I just want to point this out, and we'll get into a lot of this stuff when we do additions and other kinds of arithmetic. What is interesting is that this is only going to happen with signed instructions. If you use the unsigned version of store byte, it never sets the overflow bit. So it depends on what you're doing. Like, what is your intent? How do you want to use these numbers? So, you would be using an unsigned version or a signed version. Okay, thanks, Jason. Okay, let me just do one more instruction, which is this next one. This is a special instruction that we did not read in Knuth yet. And in fact, we won't read it till much later, but I need it for the program to work correctly. And this is the put instruction. The put instruction allows you to set one of the special registers. The special registers cannot be set or loaded into by the regular instruction. So this is a special instruction. It's saying set the RA special register to 0. And the reason I'm doing this is because the overflow bit was set. If I want the subsequent instructions to proceed, and I want this RA to indicate what the status is correctly, I need to first clear it. Because if I don't clear it, that value will remain there and I may get confused later on. Like, when was this status set, So I'm just going to do that, and that will clear RA back to 0. So that's about it. There's a whole bunch of other store examples in here for words and tetras and octas. Every single instruction that you read about so far, it's covered in this file. So yeah, if you get the chance, play around with it, step through this. We'll go into more of the debugger features and more of the assembly language features in each subsequent meetup. But again, as I said, I believe in 4 meetups we will have done enough to pretty much be pretty familiar with MMIX and its assembly. So yeah, I'm gonna hang around. So if you have any more questions or want to talk about things, that's fine. But we will continue next Saturday. I've already posted the next couple of meetups, and hopefully next Saturday we'll have understood enough that we can actually try some of the exercises as well. So I'm also hoping for that. But yeah, great. So should we call it a day? If there's no more questions, thank you so much for coming. I know this is like really dense stuff, and so thanks a lot for sticking through this for all of us, and we will continue. We'll plod along. Bye. Thanks, Deepa. That's great to hear.